Okay, welcome back everyone to this tutorial series on the theory of computation. So in this tutorial, we'll be talking about our very first concept related to the theory of computation. So this is no longer mathematical preliminaries, it's actual real material. And what we'll be looking at today is one of the fundamental uh, building blocks in theoretical computer science and in the theory of computation. It's the notion and the concept of languages. So languages are at the heart of automata theory. We build automata, which I'll define in the subsequent tutorials, specifically for languages. And so it's very important that we understand what exactly a language is so that we can then move forward and look at more complex notions related to this topic, such as automata and things like reducibility and computability. Okay, so well, I already talked about what the plan for this video was going to be. It's going to be about languages. So let's dive right into it. So first off, let's give ourselves some definitions so that we're working on the same page. So the first thing that I want to define is the notion of an alphabet. So an alphabet, which is typically denoted by capital sigma, is a finite set of symbols, or also sometimes we say of letters. Okay, and so what's important for an alphabet is that each symbol is more or less atomic. So for instance, here I have an alphabet which just so happens to be the English alphabet, from A, B, C to Z. But another very common alphabet that you'll be seeing throughout this topic is the alphabet, the binary alphabet, 0, 1. Right? So this is another possible alphabet. There's this additional restriction that I've added to the definition that says that an alphabet must contain at least one symbol. So in some textbooks, this isn't actually a specified requirement, but it just makes sense for an alphabet, for it to be useful to anyone. It makes sense for it to contain at least something, right? So if you had uh, the alphabet as, the empty set, it's as if, let's say you wanted to type something on your computer, it's as if your keyboard had no keys, right? So that's not going to be very useful. And so instead, we typically say that an alphabet is non-empty. So you can think of an alphabet also as, like I just said, the keys on your computer keyboard. So let's say here, I can either press 0 or I can press 1, right? And so then on my screen, I can have 0, 1, 1, 0, 0, 1, and so on. So that's what an alphabet is. It's the basis of what provides you with things to write, right? So it's the set that gives you the symbols which you can use to write out things. And what are these things that you write out? Well, these things that you write out are known as strings, right? So I'm sure if you've taken any kind of programming class, you've heard of the concept of a string. And so formally, for our purposes, the definition of a string is a sequence of symbols from a given alphabet sigma. Okay, so for instance, if I'm given the alphabet AB, then the string ABBA is a well-defined string over sigma, meaning that if you give me a keyboard with just A and B, I can type out this string, right? I can type out this string ABBA. But if I tell you, okay, now I have this other string ACB, well, this C is something that's not recognized by your current framework, by your current system, right? And so this string is not well defined over this alphabet. Okay, and finally, we get to what we're actually going to be very interested in talking about throughout this topic is the notion of a language. So a language L is simply a set of strings defined over an alphabet sigma. So for instance here, if I'm given the alphabet AB, then my language L, which is the set of strings A, AA, AAB, is a finite language containing specifically 3 strings, okay? I have another example here where I'm given the same alphabet, but this time I wrote down the language A to the N such that N is greater than 1. And so already I'm going to give you like a sneak peek at some of the operations that you can see in languages and in strings, and it's going to be in this case, it's going to be the exponential operation of strings, which really just means that you concat a n times. So for instance, a4 doesn't mean a to the 4. It's not an exponent, a numerical exponent. It's a shorthand for concatenation. So A4 is the same as AA, AA. Okay, and so this language here, this language L, is actually then all of the strings containing sequences of A's, where those sequences of A's are at least 2 or more in length, right? So I have AA, I have AAA, I have AAAA, and so on, right? So this is an infinite language. Another interesting one that I don't have written here is actually if I'm given the alphabet A, B, C, all the way to Z. So I have the English alphabet, right? Then a language that could be defined over this alphabet could be L is defined as the English set, the set of English strings. That's right. That makes more sense. The set of English strings, right? So if you take all of the English strings and you put them in a set, and of course I'm ignoring special strings like strings with hyphens or strings with apostrophes or proper nouns and stuff like that. If I just use the alphabet from A to Z, which is lowercase, all of the English strings, all the English words that can be written with this alphabet form a language, right? And this language is English, right? And so you can see that there's actually a very concrete meaning to these definitions, and it's not just a coincidence that we're using the term language here for a set that's containing strings, right? It's for a specific purpose, and it's because it's not the same, but it's connected to these other similar ideas of the English language or of any kind of natural language. Okay, well, that's enough rambling from me. This is essentially the definitions that you need as building blocks for understanding strings, languages, and operations on strings and languages. So now let's actually look at what you can do with these strings and with these languages. So first off, we're going to start off with operations on strings. So if I'm given strings W and V, where say W is the sequence of symbols A1 to AN, and V is the sequence of symbols B1 to BM, which are both defined over some alphabet sigma, then we define the following string operations. So we have the string concatenation, W concat V, which is essentially just you take the string W, right? So this is W, and then you append to it the string v. So this is v here, right? Okay. The other operation is the string reversal. So the string reversal is what you would expect it to be. It reverses your string. So the very last element of your string becomes the very first, the second to last becomes the second, and so on until the very first element of your string becomes actually the last element in the reverse. And finally, this isn't actually an operation, it's more of a property. So if you want to denote the length of a string, i.e. the number of symbols that that string contains, then you typically denote this with two vertical bars or two pipes in between which you have your string. So here, my string W has n symbols, and so its length is n, whereas my string V has m symbols, and so it has length m. Okay? All right, so that's operations on strings. The next important concept or string to talk about is the empty string. So the empty string, which in some textbooks is written lambda, in other textbooks it's written epsilon, it doesn't really matter, it's doing the same thing. The empty string is defined as the string with length 0. So in fact, it's the unique string with length 0. So in other words, if you ask for the length of the string lambda of the empty string, then you'll get as an answer 0. And so that's how you define the empty string. Equivalently, if you're talking in programming terms, if you think of any language like Java or Python, you can create strings with quotation marks, right? So let's say if I created a string in Python, cat, then what I would have to do is, create a variable x and then assign it to open quotations, cat, close quotations, right? So that would be the string cat. But now if I want the empty string is just, if I open the quotation marks, and I don't put anything in between the opening and the closing quotation mark, that's an empty string. And so it's the equivalent idea in theoretical CS. It's the same idea, you just have no symbol. So the absence of symbol is how you define the empty string. And so, for instance here, if I have the empty string, what happens if I reverse it? Well, if I reverse a string that has no symbols, then of course I get back the same string. I get the empty string. Okay? And the same thing happens if you append the empty string to a string W, or you concatenate W with an empty string. This will still give you W, right? Because it's like you're taking the string W and you're adding to it no symbol. So of course you get back W. Okay, so like I mentioned in the very first slide of the few definitions that we saw, there's another operation, the sort of, this is very loose, the exponential. This isn't a very formal term. So the exponential concatenation, okay, I just kind of invented that, but essentially, instead of writing down the concatenation of, let's say, a string v n times, to make things more compact, I just write v to the n. But really, you don't have to write it, you don't have to read it to the n, you could just say v concatenated n times. But I might actually just say to the n because it's quicker to say. Okay, so that's great, right? So v to the n is concatenating v n times, but what's v to the 0? Well, we're going to set up this convention where we define v to the 0 as being equal to the empty string, okay? Why? Because it's similar to how when you're dealing with polynomials, if you have a polynomial x, well, I guess in this case a monomial x, and well, actually, you just have a variable x. It's not a monomial. You have a variable x, and you exponentiate it to the 0, then this will always give you 1. And so I'm being very generous here. I'm not considering 0 to 0. Let's say x is not 0. So, I should have taken a more specific case. So 5 to the 0 is 1, right? So it's in the same vein as that kind of convention. So v to the 0 is your is the empty string. Okay, it's the equivalent sort of identity element, right? So the empty string is kind of like the identity string. Okay, and then there's another example here. So if I have W is AB and V is BA, then what is W2, V2, W0? Well, it's just W concatenated twice with itself, so AB, AB, and then concatenated with V twice, BA, BA, and then W to the 0 is lambda, but then if I concatenate lambda with any string, I just get back that string. And so this is my result. Or if you want to write it more compactly, you could have also written this, right? Okay. So that's exponential concatenation, quote unquote. The other concept about strings that I want to talk about, which is going to come back in a few videos from now, is the notion of a substring. So if I have a string z, okay, then I say that that string z is a substring of a string w if it appears consecutively within w. So for instance, if I have the string w is ABAA, then a possible substring could be BAA, right? So this could be a substring. So this is W, and BAA is a substring. What could be a substring, right, would be something like, let's see, I can't, so if I had, for instance, if I had, I see. Okay, so what couldn't be a substring could be something like A, right, AAA, right? So if Z is equal to AAA, even though there's 3 A's in my string W, they don't appear consecutively in W. And so this string is not a substring of W. Okay, so the consecutive part is very important. And these two examples are actually more of counting problems, so I'm not going to spend too much time on this, but I encourage you to sort of think about it on your own just for extra practice. Okay, and specific types of substrings also exist. So, for instance, a string X is a prefix of a string W if there exists a string Z such that W is equal to X concatenated with Z. So really this is just saying that X is a prefix of W if X appears at the beginning of W, right? And X is a suffix of W if it appears at the end, consecutively, of course, right? So there's this implicit idea of the string always appearing consecutively. So for instance here, my string is A, B, B, A, right? What are some possible prefixes? Well, AB is a prefix, ABBA is a prefix. What's not a prefix is, let's say, so these are prefixes. What's not a prefix is, let's say, BB, right? So BB appears here, okay? But it doesn't appear at the very beginning. Like the first symbol of the prefix has to start the whole string, right? So that doesn't occur with BB. So you can find a bunch of examples that are in prefixes, and then similarly for suffixes, right? So what are some suffixes? Well, it needs to sort of end with a, right? So it needs to sort of you need to have one one end at a here and the other end somewhere else to the left of the string, right? So for instance, I could have BAA as a suffix, right? So this could be my suffix. I could also have, let's say, the whole string could be a suffix of itself, right? So W is a suffix of W, and W is a prefix of W, right? What's not a suffix though is, again, the same thing. Let's say BB and then A, right? So BB and then A. So I have BB and then I have A, but I'm kind of like skipping this A. So then that's not even a substring of A actually. So uh, actually it is a substring. So BBA is a substring, but it's not a suffix. I wanted to find one that even just wasn't a substring. So let's say, in this case, A. So this isn't even a substring. So of course it's not a suffix of the string W. Okay, now I have a few more examples. I'm not going to belabor them. I want to keep these videos relatively short. The next thing is that I want to talk about. Actually, you know what? I think it's a good place to stop. So let's say this video was about introducing these concepts formally and looking at operations on strings. The next video is going to be operations on languages.